If I just posted keys.
Oh, yeah.
You like peach jelly. Yeah. All right. So what I was talking about in that last homework problem was finding the derivative. Because that whole process using this limit as h goes to 0 is you're finding the derivative. Right? That's what we were doing. We were using the difference quotient to find the derivative. But the cool thing about part A to part B was that I found the derivative, and then part B was super easy because all I needed to do was just plug in those x values. And that was giving me the slope at different times, right? So this whole lesson that we've got here today is basically like saying, well, yeah, we could find the slope at one point, but really we could generalize it. We could generalize it and then say, we could kind of make the derivative an equation in and of itself. And just saying, okay, here's the function that is the derivative. You give me an x value, I'll pop out a slope. You give me the x coordinate where you want that slope to happen, and I'll tell you what the slope is along my graph. Okay? And that's what we're talking about, the derivative as a function. In the preceding section, we considered this, the derivative is equal to the difference quotient, right? And that's what we did on the last problem. Here we change our point of view and let A vary, meaning we're going to let A be anything we want it to be. We're going to let A be x in this case, because essentially isn't x the same if I'm plugging, like it's still the location where I'm finding the slope, right? That location doesn't change if I plug it into f or if I plug it into f prime. The location is when I plug it into f. The slope is when I plug it into f prime, which is the derivative. So here we're changing our point of view and we're just replacing a with x. That's the only difference today. All we're going to do is say, let's let it be general. Let's let x be anything it wants to be. Let's plug in x into this difference quotient, and now we can evaluate a function for our derivative. We can say at any given point on this curve, I can pop out the slope just by telling me the x value where we want it to happen. Given any number x for which the limit exists, we assign f prime of x, so we can regard f prime as a new function called the derivative of f, right? We're going to write it as a derivative. We know that the value of f prime at x can be interpreted geometrically as the slope of the tangent line to the graph at any given point. So let's take a look here and evaluate a graph. Now, what's going to be very important is not only just the function of the derivative, but if we're calling the derivative a function in and of itself, can't we graph a derivative then? Here's what I mean. Here's my function f. Here's my function. We're going to use it to sketch the graph of f prime. So let's pick out some points. Let's say, let's pick out right here, right here, right here. Yeah, maybe another couple points if we need it. Let's call this 0.5. What is f prime of 0.5? What is f prime of 0.5? Now, what am I really asking you? I'm really asking you, what is the slope of the tangent line at 0.5? If I drew a tangent line, what would the slope be? What do you think the slope would be? What's the slope? 0. That's 0, right? Not undefined, that's undefined. If I drew a tangent line right here, the slope of that tangent line, which I'll draw it on here for the video, would be right there, right? So the slope is of that line 0. That just gave me a coordinate. I know on the graph of my derivative, I've got a coordinate 0.5 comma 0. Okay, so let's call this 1.5. So what is f prime of 1.5? 0. What is f prime of 3? 0. Okay, what did I really pick out here on the graph of f? Didn't I pick out my maximum and minimum points? Right? I picked out my maximum and minimum points, and the maximum and minimum points were actually where the derivative was equaling 0. Now, what are these coordinates on the derivative? A number comma 0. A number comma 0. What am I identifying here on the derivative? The x-intercepts. So here's one of the huge connections that we have to make. The graph of f. If I look at the graph of f and I find the maximum or minimum points, those locations are the x-intercepts of my derivative. Okay, meaning this: if I go to graph my derivative, right? Actually, I should go a little bit low too. Yep. If I go to graph my derivative, I know at 0.5. I'll make this 1, 2, 3, 4. Kind of went a little above that anyway. At 0.5, I have an x-intercept. At 1.5, I have an x-intercept. And at 3, I have an x-intercept. 1, 2, 3. Now, what happens in between there? Well, think about this. The slope of the tangent line in here, what can you estimate that to be? 1-ish. Something positive, right? But it looks like it's about 1. So at 1, we have the coordinate 1. Let's go 1, 2, 3, 4. Sure. Well, that's really spaced out evenly. 1 comma 1. Okay, what can you estimate the slope to be? Let's go like here, right in the middle. Let me ask this question first. Is it positive or is it negative? Negative. It looks kind of steeper than 1, right? Maybe, let's say negative 2. Negative 2. Let's ballpark it, negative 2. So at, let's say, call this 2, we are at negative 2. So I guess I should have made my graph go a little bit below the x-axis, shouldn't I? At 1, 2, 2, sorry, this is at 2 comma negative 2. 1, 2, negative 2. Okay. And what do you think my slope is here? Looks like it's about 1 again, right? Don't you think these lines kind of look parallel right here? Yeah. So yeah, it looks about 1. So at 4, looks like it went back up to 1. So here I can graph my derivative. There's the graph of my derivative. Okay. Now, what is this telling me? Man, we are going to spend a long time, a lot of this year, focusing on the difference between the graphs of f and f prime and how they relate to one another. There are a ton of different correlations here. Like, for example, the first one that we picked out, the maximum and minimum points of f are the zeros of f prime. Another thing here, look at the slopes here. If I draw any sort of slope here, that's a negative sloping line. Look, it ends up below the x-axis. Any sort of positive slope in between here, that's why it's positive here. So anywhere where it's increasing on f, it's going to be above the x-axis on f prime. Anywhere where the function is decreasing on f, it's going to be below the x-axis on f prime. Okay, there's a lot of different tie-ins that we have here. All right, so let's take a look here. If f of x is equal to x to the third minus x, find the formula for f prime of x. Boo. And the reason I say boo is because they gave us an x to the third. Lame. Lame. Could have illustrated it just as good if it was x squared minus x, but I will comply, I will follow directions. X to the third minus x. Find a formula for f prime of x. Okay, so f prime of x is going to be the limit as h goes to 0 of f of x plus h minus f of x all over h. The reason I say boo is because now some of you see it. This has got to be x plus h to the third minus x plus h. At least we don't have to do it squared as well. Minus f of x. So x to the third minus x. One place where a lot of you will get thrown off is forgetting to put f of x in parentheses, because you have to distribute the negative. It's subtracting the entire function f of x. Okay, what do I mean by that? This piece right here. You always have to put f of x in parentheses because you're going to distribute in that negative, all divided by h. All right, okay. So x plus h to the third. I mean, we could use Pascal's triangle to figure this out too. I'm just saying. 2xh plus h squared times x plus h. Right? So all I did was square it first, and now I'm going to multiply in by x plus h. All right, so that means I've got x to the third plus 2x squared h plus xh squared, just distributing the x. And now let's distribute in the h. Plus x squared h plus 2xh squared plus h to the third. Okay, so that will be x to the third. I've got a 2x squared h and a no, that's different. 2x squared h and a 1x squared h. So all said and done, 3x squared h. And then I've got an xh squared and a 2xh squared. All said and done, a 3xh squared plus h cubed. Oh, sorry. Now I've got to subtract away. See, this was just the x plus h to the third. Minus x minus h, right? Got to go here and got to go here. Minus x cubed plus x. That's all divided by h. You just got to keep your work organized. Honestly, that's one of the hardest parts about these problems. If you're one of those people that has their work all over the place, good luck. Clean it up. Okay, we got x to the third and negative x to the third. Looks like we've got a negative x and a positive x. See that one in there. Anything else? No. Which is good anyway, because everything has an h in it. So 3x squared h plus 3xh squared plus h cubed minus h, all divided by h. And now let's take out that h. So 3x squared plus 3xh plus h squared minus 1. And now we say the limit as h goes to 0, which means that's going to go to 0 and that's going to go to 0, which is equivalent to 3x squared minus 1. And that, my friends, is f prime of x. The second part about this says illustrate the formula by comparing the graphs of f and f prime. I would do that if I had a graphing calculator, but honestly, all you need to do is just plug those in your calculator and look at them and see. I was just going to talk again about how the slopes of f relate to the graph of f prime. You know what? Why don't I just jump on Desmos real quick? DES. Desmos. So here is, let's learn together. Oh, I should just click on graphing calculator. Darn it. Oh well. Graphing calculator. I've got x to the third minus x, right? X, shift 6, third. Whoa, that's x to the fourth. X to the third minus x, right? Oh, get out of there. Minus x. And then what was my derivative? 3, I don't even have to look at it. 3x squared, shift 6 squared, minus 1. Let me zoom in a little bit. There is one whole section in chapter 4 where we compare the graphs of f and f prime and f double prime to and see what the variations are. Okay, so this is f. This is f prime. Okay. So what do you see here? Well, look at this. This place here and this place here. The maximum value of my original is the 0 of my derivative. The minimum value of my 0, or of my original, is the 0 of my derivative. Do you see that in there? Everywhere where I am increasing on f, the function is above the x, the derivative is above my x-axis. Everywhere I am decreasing on f, it is below the x-axis. The derivative is below the x. Everywhere I'm increasing on f, it is above the x-axis. The derivative is above the x-axis. There's a lot of different things that we can look at here. One other really cool thing, look at the minimum point of my derivative. Let me just get all this junk away so we can really focus in on this. This is where we will end. The minimum point on my derivative. How does that relate to my original? I know it's running through 0, 0, but what is the shape of the graph doing at the 0 of my derivative? F is my original, and f prime is my derivative. So the 0 of my, the minimum value of my derivative, look what's happening at my original. This is where the function is going from concave downward to concave upward. Okay? That point we will learn later on is called an inflection point, where the direction changes. Okay? Where the slope of the tangent line goes from the slope goes from decreasing actually back to increasing again. So it's actually talking about the rate of change, the double derivative. But we'll get there.